So first of all, I'd like to welcome everybody to 19 Washington Square North, which is the home and intellectual center of NYU Abu Dhabi here in New York. My name is Michael Puruganan. I'm a professor of biology here at NYU New York, and I also run a laboratory at NYU Abu Dhabi, where I also serve as an affiliate faculty. So, and for the reason for that is I'm also now the academic director here at 19 Washington Square North. So welcome everybody to 19. Over the course of the academic year, 19 is host to many interesting lectures, seminars, conferences, conversations, where we try to tackle many of the important issues of the day and to educate the NYU community and the public at large in many different topics of interest to them. Many of the topics here or the meetings and conferences are organized by the NYU Abu Dhabi Institute in New York and Abu Dhabi, which is led by my colleague Sharon Hakaken-Bergman here, who is the Director of Academic and Research Programs, and with her staff, she puts together many of the programs we see here at 19. Today we have a special lecture that is part of what we call the Luminaries of Science program, where we invite this distinguished scientists to give lectures on topics of general public interest. This is timely in this day, especially because this year, the United Arab Emirates in Dubai is host to COP28, the climate conference. And so for the entire year, we do have programming that's around issues of climate change and sustainability. So without further ado, I'd like to turn it over to my colleague, David Holland, who will introduce the speaker today.
Thank you, Michael. It's a pleasure to reintroduce Gavin here, or introduce Gavin. Gavin's a good friend of mine. I met Gavin, I think it was so I left McGill University in early 90s, and 2 months later, Gavin showed up as a postdoc at McGill, so we kind of missed each other there. Gavin did his undergraduate at Oxford, and then PhD at UCL as basically a mathematician. And I'm not sure climate was on his radar at that point. No. Then he moved to McGill, working with my PhD supervisor, Lawrence Mizak. Then I ended up at the Earth Observatory at Columbia, and I had thought Gavin was also working there, but it was just that he was hanging out there. He's actually had a NOAA postdoctoral fellowship, very nice fellowship, prestigious, and he was started at NASA GISS, but he would hang out at Earth Observatory because it's a fun place to do science as well. And Gavin has since been at NASA. Most all of you know Jim Hansen, or James Hansen, and the work he did at NASA leading that group. So Gavin now has that position, lead position at NASA GISS. Yeah, he's filling his shoes, isn't he? He's filling James's shoes and doing a fabulous job. A lot of you might know Gavin through the press, TED Talks, a book and things. He's really made an effort, which I think he genuinely enjoys, is talking about climate. And as a mathematician, he kind of transferred over to climate and has had a big impact in our field. He's a fellow of the American Association of Advancement of Science, American Geophysical Union, all very prestigious, select, if you will, appraisal or appreciation for his efforts. So jumping to today, I think I've covered most of those points. Certainly my part, I work in Antarctica and I see big observed change, and I wonder about the understanding of it. So this title kind of really intrigues me. And it's got to the point now when we look at the Earth environment, we hear things now this past year, record temperatures. We're breaking lots of records, fires in Canada, gone crazy elsewhere, et cetera, sea levels changing. So it seems like a lot is happening, perhaps accelerating. And I think maybe that's a little bit of what Gavin's referring to, everything we see around us. And perhaps he's going to discuss that and perhaps shed a little bit of thinking about the understanding of that, which is perhaps a very important part. So it's a pleasure to have you here, Gavin, and let's go. And Gavin said you could have, if you have a burning question, go for it.
All right. Thank you very much. Okay, I had to do the technical thing of plugging this in. And it should just work. Ha! It did. Incredible. Who says modern technology is useless? Anyway, thank you very much. Thank you very much, David. Thank you very much for NYU Abu Dhabi for inviting me. When I saw the email, NYU Abu Dhabi, like, oh, that's a long way to go for a talk. But it turns out not to be so far. So, so that was good. Yes, I live mostly uptown, so coming downtown is very, very strange. But you know, but not uninteresting. You get to meet interesting, you know, the locals. So I'm gonna talk about what's happening now. And to understand what's happening now, you have to go back a little bit to what we understood was going to happen, and then we have to think about what this means now. And so, what's going to happen? And so we're gonna try and cover a little bit of the past, a little bit more of the present, and then a little bit of the future. So here are the main questions that's a kind of like underlying what we're talking about here. So are things changing? And by things, I mean climate. Is climate changing faster than we predicted? How are our predictions evolving? How are things that we predicted 10 years ago, are we still predicting the same things? How are those things changing and evolving? And what's actually going to happen, right? I think that's really the underlying point of what we care about. So those are the three questions that are going to animate what we're going to talk about here. But let's be clear, things have changed, right? This is an old photograph from the 19th century, late 19th century, the Mendenhall Glacier in Alaska. You can go to this exact same point where this photograph was taken, and you can take a new photograph. And you can see that things have radically changed. And everywhere where there's ice on the planet, you can go and do this same thing. You can do this in the Rockies, Glacier National Park. You can do it in the Andes, in the Alps. You can do it in Kilimanjaro. You can do it in Papua New Guinea. Did people know that there were glaciers in Papua New Guinea? Yeah, well, not anymore. No. So you can, all of these places, you can go and you can see the changes, right? So something is happening. We can use like very clever technology to see what's happening as well. And so one of the things that is an incredible piece of technology are the GRACE satellites. And these are two satellites that fly around the Earth, and they measure the Earth's gravity, how much the Earth is sucking. And right now it sucks a lot. So, but you can also see how it's changing, right? So these satellites, they go around the Earth and they just measure how close they are to each other. And when they go over something that's very heavy, like a big mountain, they get a little bit closer together. And when they go over the ocean, they go a little bit further apart. And so when they go in and out, you can make a map of where the gravitational hotspots of the planet are. And the planet is it's not a smooth ball. It's a very dimpled thing in gravity space. But we've been looking at the gravity of the Earth now for more than 20 years, and we can see how the gravity is changing. So how does gravity change? It's not some magical cosmic thing. Gravity changes because mass moves around. What's the mass that's moving around on the Earth? Water. Water moves around on the Earth. It's sucked out of groundwater and put on the fields and ends up in the ocean, and it's melting from the glaciers and from the ice sheets. And these two maps that you're seeing here are the maps of where the gravity of the ice sheets is changing. So all the places in red are where the mass is going, and the blue is where the mass is gaining. But it turns out that the loss is much bigger than the gains. And so both in Antarctica and in Greenland, the total amount of ice is going down by hundreds of billions of tons of water per year. And that's enough to really make an impact. It makes an impact on sea level, it makes an impact on the oceanography around these glaciers, and it's making an impact to the very geography of the ice sheets themselves. Things are changing. But 2023 has been exceptional, right? This is seasonal cycle of temperature. And it's how it's been changing since the 19th century, right? So you see this, you see the blue lines. That was the seasonal cycle of temperature back in the 19th century, right? And as you go up through the colors, you're actually going forward in time. And so the red lines there, those are the 2010s, 2020s. And so you can see there's a gap there. You can see that the change, this is in Celsius, but it's about a degree and a bit in the seasonal cycle, bigger in the winter than in the summer. Things have moved. So, you know, you can see, for instance, that the Januaries now are about as cold as Marches used to be. And there's nowhere that gets as cold as Januaries used to be, right? If you've seen, I'm sure you all live in New York, so you know there's a lot of 19th century photographs and sketches of people skating on the ice in Central Park, right? You might have seen that. There's a reason why we don't do that anymore. The ice does not get thick enough and safely enough, but it used to. They used to be thick and safe. Things have warmed up. But you can see that 2023, and that's the data up until September, so up until 2 months ago, is way above all of the previous years. And so what we can predict with some certainty is that 2023 will be the warmest year in this record. Now, we've had other warmest years, and 2020 was the warmest year, 2016 was the warmest year, 2015 was the warmest year, 2014 was the warmest year, 2010 was the warmest year, 2005 was the warmest year, 1998 was the warmest year. And one of the interesting things about this whole warmest year thing is that it sounds a little bit repetitive, right? So I do a lot of press and you know, at the end of every year, and they say, oh, was this year the warmest year? And quite a lot of times I have to say, well, yes, it was. My predecessor that David mentioned, Jim Hansen, he became very famous for declaring that global warming was here back in 1998. And at the time, that was a very warm summer. And in fact, 1988 was the warmest year on record up until that date. The interesting thing is that doesn't seem so long ago, but that's now the 27th warmest year. Things have changed. This summer was particularly warm. These kind of maps, you can see that there were heat waves and exceptional warmth pretty much across the Northern Hemisphere, around in South America, Alaska, Europe, Australia. All of these places saw record warm temperatures this summer. And that has impacts. That has impacts not just on temperature and heat waves, as you might expect, but it also has impacts on things like intense rainfall and fire and things that really make a difference to how we feel and experience climate. This is not just an academic exercise. Now, this is a university, and so we're all quite fond of academic exercises, but this goes beyond that, right? This is a time series of the temperatures since the late 19th century. It's 4 different estimates of how things have changed. They use slightly different data, slightly different methods, but you can see that they're all pretty consistent. Particularly since the 1960s, they're pretty much in lockstep. As you go back further in time, it becomes a little bit harder to estimate what's going on because we don't have quite as much information. But you can see that you know, things were pretty flat through to the 1920s. They warmed a little bit to the 1940s, and they cooled a little bit from the 1940s to the 1970s. But since the 1970s, we've seen this relentless warming of the climate. Some of those ups and downs are because of El Nino events, La Nina events. Some of them are because of volcanoes that went off. There's like 3 or 4 volcanoes in this record that you can pull out if you want to. And it's important for us, I think, to get a grasp of how big this is, right? So how big is this, right? So this is Celsius on one side, right? So you know, we're scientists, so that we know what that means, but normal people don't, right? So 2023 is going to be up there. That's about 2 degrees Fahrenheit, which is like a more normal unit for folks in this country, at least. Did you see the SNL sketch the other day? There was a great SNL sketch with George Washington, like talking to his troops, and you know, declaring what it was that they were fighting for. And one of the things they were fighting for was to have measurements that made no sense at all. But why? Nobody knows. It's go and check it out. It's actually quite funny. Anyway, so it's 2 degrees Fahrenheit since the 19th century. Now, does that seem like a big number? It's okay. You can tell me. Does that seem like a big number? It's contextual, right? Do you think it's a big number? Yeah, that's okay. You can tell me. Yeah, do you think it's a big number? 2 degrees Fahrenheit? Could be a big number, couldn't it? Yeah. So let's compare it to things, right? So we're all sitting in a room here. It's air conditioned, but we're all generating about 100 watts of heat putting into this room. This room has probably warmed by 2 degrees Fahrenheit since we've just been sitting here. And as far as I can tell, nobody has gone extinct and nothing has melted, right? Okay, we're good. But is that the right scale to be thinking about this? No, we're not talking about a room. We're not talking about a town. We're talking about a planet. So how much does temperature on a planet change? Well, we've had changes in the past. I mean, this planet has gone through hot houses and cold houses and snowball Earths and ice ages. So we can go back to the last ice age, right? So the last maximum of the ice extent was about 20,000 years ago. And at the time, New York was covered in ice, hundreds of meters of ice. And that glacier stretched all the way from the Arctic Ocean, all the way across Manhattan and stopped in Brooklyn, just by coincidence. And you can see the terminal moraine of the last ice age in Prospect Park. So if you go into Prospect Park and from Grand Army Plaza and you kind of go through the little tunnely bit and you look down over the grass, you can see 2 little hillocks kind of halfway down the thing. That's the terminal moraine. That's where the edge of the ice sheet got to. And that ice sheet was pretty much solid from there to the Arctic Ocean. There was so much ice wrapped up in that ice sheet that sea level fell by 400 feet, right? That is an enormous amount of ice. For hundreds of miles to the south of here, it was tundra. No forests, no pines, no you know, nothing apart from mosses and ferns, perhaps. Mammoths, cavemen, the Ice Age, very, very different planet. How much colder was the Ice Age? Anybody want to? I'm trying to build a little tension here. I'm trying to like get people to, and then he just tells you the answer. Okay. So see, this is better. We could have started with you. Yes, 20 degrees, and then somebody else would say, no, that doesn't seem cold enough. Give me 40 degrees. There we go. See, like, and then you would come in and say, oh, 9 degrees. Okay, so the answer is 9 degrees, right? Only 9 degrees Fahrenheit separated the Ice Age from the climate that we used to have, 9 degrees Fahrenheit. And so that was something, if we compare that to the 2 degrees Fahrenheit change that we have now, right, that's happened just in 100 years, that 9 degrees warming out of the Ice Age took 10,000 years to happen. And if you compare that 2 degrees to the 9 degrees, and you think about it in this context, that's about a quarter, maybe a fifth of an Ice Age, but in the other direction, right? So now, is 2 degrees Fahrenheit a big number? Little kid was right. Yes, it is a big number. And it makes a difference, right? It's making a difference to sea level. The melting of the glaciers, the melting of the ice sheets is raising sea level. The sea level itself is rising because the water itself is getting warmer, and warmer water expands and it fills the bathtub a little bit more. Oh yeah, yeah. I mean, but not very much. Over say 100,000 years, there was a few degrees of temperature change. And then 125,000 years ago, it was slightly warmer than it is now. So the ice age cycles happen on these like kind of 100,000 year timescales, and it would be very cold, warm, very cold, warm, etc. But we're now outside of that. We would be right now. We'd be in a kind of stasis, but kind of a flat period. People have speculated, or not so much, but people used to speculate about the length of the interglacial, right? So the Holocene has lasted about 10,000 years. The last interglacial lasted about 10,000 years. And so back in the 1970s, people started to get a little bit worried that maybe this interglacial was only going to last 100,000 years. And so people were looking for signs of an incipient ice age, which were not to be found. But it turns out that if you go back further, the interglacials have lasted multiple different lengths. So 10,000 years, 30,000 years, 50,000 years, kind of paced by one of the other orbital cycles. And so right now, without our input, one would have anticipated that we'd be in a kind of a 30,000 year interglacial. So we'd be pretty stable where we are right now. So the sea level is rising. And one of the things that happens with sea level is that even if the sea level rise is smooth and apparently not very large, the amount of flooding that it generates increases exponentially, because you're getting more and more events that go across the threshold. And so we're seeing exponentially increasing flooding days around the United States, particularly along the East Coast, which is a hotspot of sea level rise. So from kind of Key West, Miami, the Carolinas, places particularly like Newport, Hampshire, Virginia, Chesapeake Bay is another hotspot. And then until you get up to Maine, where it kind of flips over. How do we go about understanding all of these changes? What are our tools? What's our toolkit for making sense of this? Some of you might recognize this, maybe you. This is a punch card. This is how you used to program computers. Before there were screens, before there was graphical interfaces, before there was even keyboards, this is how you programmed a computer. You would punch this out, and this would be one line of code. And each of these sets of things would be one subroutine. You have to put it in order, and then, like, you know, if you messed it up, it would go all horribly wrong. If you dropped it on the floor, it was a disaster. And it would take literally months to do the simplest thing. This is the beginning of climate modeling. This is in fact a line from an old climate model, the old GISS climate model that was first written in the late 1970s. And it was written in Fortran, which is an old computer language that nobody knows anymore, but our codes are still in Fortran, so that's a little bit of a problem. But we no longer use punch cards, thankfully. You know, we've caught up with typewriters and other fancy technologies. But models and code have been the way that we have broken into this, the way that we have used to understand what's going on. Climate modeling itself has been a process, right? It started off in the 1950s and 60s, very simple approximations, and mainly just confined to one element of the climate system, right? The atmosphere, or the ocean, or the ice sheets, or the carbon cycle, very simple models. But people realized over time, and as available computing increased, people realized you needed to, you know, what happened to the atmosphere was not independent of what happened to the ocean. What happened in the ocean was not independent of what happened in the ice or in the cryosphere. And on land, it was not independent of what happened in the atmosphere or even in the ocean thousands of miles away. And so that realization that all of these things are connected and that the climate system itself is more than the sum of its parts, that realization has taken many years to come to fruition. And so it's a little bit like it's a little bit like the Borg, right, in Star Trek. And I apologize for the people who were born after 2000. The Borg were this alien entity that would just assimilate other civilizations, and they would become part of the Borg. And climate science has become a little bit like that. Climate models have assimilated all of these other fields, such that all of these fields are now climate science, whether they like it or not. And we now have a situation in the 2020s where we have very functional models that include perhaps not every single thing that matters, but almost all of the things that matter for understanding climate change. So how do we develop climate models? How does that work? Well, we start off with the basics of the planets, right? Where are their continents? How high are the mountains? What kind of soils do you have? Where are the ice sheets and things? We build in the physics of the system. So these are conservation laws, conservation of mass, conservation of energy, what we think clouds do, how we think rain forms, what we think soil water does, and how we think evaporation works. All of these things that we can go into the field, measure, encapsulate, and try and put into these models. You put that all together and you have something that looks a little bit like the real world, but then you really want to make it look a little bit more like the real world, so you can kind of tune it. There's some free parameters that you don't really know what they are. We have to approximate those things. We're using relatively sophisticated machine learning techniques now to do this. And then we end up with a simulation of the real world that we can then compare to the real world. And what we find is that over time, we get better and better at matching what we see in the real world. The clouds, the rainfall, the temperatures, the radiation, everything that matters for the climate, we can try and compare to observations. But these are models, right? They're always wrong, right? But we want to make them better. And so we find the things that are wrong, and then we start all over again, and we go through this cycle over and over again, which is great for my career prospects because there's no end. In fact, the models are never going to be perfect. And so we can keep on going through there. And it's frustrating for everybody else because the models are always about to get better. They're always not quite there, but they're always about to get better. And our understanding, what we interpret from these models, what we apply to the real world, it does develop. These models become more and more useful, even if they're not perfect. So what do they look like? Right? So this is an animation that's been drawn from a climate model. And what you're looking at here are the particles in the atmospheric circulation. So the orange particles, that's dust that's come off here from the Sahara. That white wispy stuff, that's air pollution, sulfate pollution from burning of fossil fuels. You can see some of this blue stuff over the ocean. That's sea salt that's being pushed into the atmosphere by storms and waves and breaking things like that. You can see these red dots. Those are places where there are fires. Fires produce a lot of biomass burning emissions. So these are carbonaceous aerosols, soot, those kinds of things, organic aerosols, those go into the atmosphere. And you can see that the model is producing here. There's some tropical cyclones that you can see that are pulling an enormous amount of sea salt out of the atmosphere. And everywhere you look, you can see these particles being pushed and turned and manipulated by the weather systems themselves. Here, so you can see the storms going around Antarctica, and all of these things are being pushed around by the weather. But because we can actually see them, because they interact with the radiation from the sun, with the radiation that comes from the ground, they're actually affecting the weather themselves. And so what you have here is a very, very complex dance where everything effectively affects everything else. Organic carbon, yeah. So isoprene, terpene, secondary organic aerosols. Oh, and did you see that? That was a volcano that just went off. Lots of things are going on at the same time. And it might even strike you that how can we possibly work out anything that's going on if everything, even in the model, is this complicated? Luckily, we're getting quite good at this. We can actually analyze this and see what is actually happening. But I just wanted to give you a sense for what these models are actually doing. So, have these models been useful? Have they provided skillful predictions for what is actually happening right now? So let's roll the tape, as they say. So back in the 1960s, we really got our first view of how the climate was changing or how climate worked well enough for us to get those first predictions. This is a prediction from Manabe and Weatherald that was published in 1967. Manabe is still alive. And you may remember his name because he won the Nobel Prize for physics 2 years ago, and he was one of literally 2 people who were working on this in the 1960s and early 70s who were still alive. And the only other person that was working on this and making predictions about climate change in the 1970s that was still alive was William Nordhaus, and he'd already won a Nobel Prize for economics. So basically, Manabe was the last man standing, but that isn't to take away anything from his insight. He was truly one of the pioneers of climate modeling. And what you're seeing here is this is the height through the atmosphere, you can see that there's 3 lines, and they're at different levels of carbon dioxide. And what it shows is that when you increase the amount of carbon dioxide in the atmosphere, they predicted that it would warm at the surface, or in the troposphere, that's the lowest part of the atmosphere. And in the stratosphere, that's above all the clouds, it would cool, which is an interesting kind of pattern, right? And this was before we really even had measurements of the temperature of the stratosphere, right? The stratosphere is not the easiest place in the world to measure because it's tens of kilometers above the surface. And we didn't really have a very good idea about what was going on. But this was the prediction that was made in the 1960s. In the 1970s and 80s, we got a little bit better at pulling models together, and we started to make predictions for the pattern of change, right? How would things change, across the globe? These are 2 very early predictions, one from Jim Hansen, my ex-boss, and another one from Manabe. And they have a number of things in common. One of the things is that the land always warms more than the ocean. The north almost always warms more than the south, and the Arctic warms fastest of all. And those were very robust predictions, again, from 40, 50 years ago. And there was one key consequence that people understood that would help us decide whether these predictions were any good. Right? How would we know if we were predicting something for the right reason, right? So science works because we predict things that are not in evidence, right? That we can then go and look for. One of the things that people predicted would happen, and this is a quote from one of Jim Hansen's papers, is the importance of the changing amount of heat in the ocean, because their thinking was that if we're increasing the amount of greenhouse gases, we're slowing the rate at which things go out to space. That means it has to warm up more at the surface. But in the meantime, there has to be more energy coming into the system than going out. And where does that energy get stored? Well, not in the atmosphere, because the atmosphere doesn't have a lot of heat capacity. The big engine of heat capacity on the Earth is the oceans. And so they said, well, if we have more energy coming in than going out, that energy is going to end up in the ocean. And so they predicted, again, before any of these things were measured, that the amount of energy being stored in the ocean would be increasing. Again, measured, stated in the 1980s. And let me just define one thing, because sometimes people get confused by this. So when I say that a model is skillful, I mean that it gives you a better answer than you would have been able to get without it, right? It doesn't mean that it's perfect. It doesn't mean that it's right. It just means that it's better than what the alternative was. And the way to think about that is in the context of weather forecasts, right? Do we think the weather forecasts are perfect? Show of hands. Actually, they're getting pretty good. But we don't expect weather forecasts to be perfect. We expect them to be useful. And so if it says that you're planning, if you're planning a party this weekend, say, and it says it's likely to rain on Saturday, but not on Sunday, and today is Monday, would you switch your day of the picnic? Would you? What if it was Thursday and it predicted it would rain on Saturday, but not on Sunday? Would you switch it? You would, right? Because we have experience with weather forecasts and we know that they're skillful, but not perfect, right? If you were to say, okay, well, is the rain going to start at 1 o'clock or is it going to start at 3 o'clock, 3 days beforehand? Would you change it to 1 o'clock to avoid the? No, you wouldn't, because you don't trust it that much. Okay, so the model can still be useful, even if it's not perfect. And so hurricane intensity is a tricky thing. We're actually getting much better at that. So I mean, if you remember Sandy, the track of Sandy was well predicted 10 days in advance, right? That's incredible. And so the skill of weather forecasts has improved enormously in the last 30 years. What was a good forecast 3 years for a 3-day forecast, it was a good forecast 30 years ago. We are now doing as well for 5- and 7-day forecasts, right? Let's circle back to that. So when I say a model is skillful, I'm not saying it's perfect. I'm not saying it's right. I'm saying that it's useful. Okay. So did those predictions come true? The answer is yes. So here's a graph of measurements of the stratospheric temperatures at the top and the tropospheric temperatures at the bottom, measured from satellites that weren't even launched at the time that Manabe made his prediction. And what we can see is, yes, the stratosphere has been cooling. Yes, the troposphere has been warming. And there are other things going on. There are volcanoes that cause the stratosphere to warm and the troposphere to cool. There are El Nino events which cause the troposphere to warm, but don't really affect the stratosphere much at all. And if you look closely, you can see some solar cycles up there at the top. There's a lot of things going on, but those basic predictions that were made came true. The patterns of temperature change were also well predicted. This is the trends since 1970 in the annual mean temperatures. Warmer on the land than in the ocean, warmer in the north than in the south, warmest most of all in the Arctic. Even the rates of change that were predicted in the 1980s were well matched. So this is an early climate prediction made in 1981, slightly underestimated how much it was going to warm. These were the runs from Jim Hansen in 1988 that bracketed what actually happened. Here are some a larger collection of climate models that were run around 2000. And again, they predicted what was going to happen with the global mean temperature extremely well. We've done it again, and we've done it again, and we've done it again. So these models have predicted the warming that we've seen. They predicted the pattern of warming that we've seen, and they predicted the stratospheric cooling that we've seen. And the ocean heat content, what happened to that? That's been increasing too. And so we have a very confident understanding that we know why things have changed up until now and why they continue to change. Now, these models have been getting better over time as we do that dance and we improve the skill of the models. And so these are different generations of models, and you can see. So The ones that are out here, those are very bad, and the ones over there are much better. And as the generations go by, there's more good models and less bad models. One of the curious things is that the average of all of the models is better than any one model, which, if you think about it, and I could go into this in more detail, is very strange. Because the average of lots of things that aren't quite coherent should be less coherent. But in fact, it's better. It's very strange. But we get used to that. And even things, this is a little technical, but the point to be seen here is that the generations, this is the light blue is the early generation, the red is the middle generation, and the dark blue was the most recent generation. And the more that it's towards the one, that's a perfect correlation, that would be great. The happier we are. And so these are the patterns of change associated with things like El Niños and La Niñas. And it turns out that we've been getting better over time, even though that wasn't something that we necessarily targeted as something that we wanted to be doing. But as the models have got better, they have become more skillful. And that allows us to give you a really good sense of how things have changed over time. Right, so there's a bunch of stuff here. Right at the top is the stratosphere again, then the lower stratosphere, then the surface, and then the ocean heat content. Over the graph on the other side is the Arctic ice, and there's 4 lines here, right? So there's the observations in black, and then there's 3 sets of model results. One where we only have the natural things going on, right? So those are the green lines. The natural things are volcanoes, the solar cycles, the small shift in the Earth's orbit. And then there's the red lines, and that's only the things that we've done. The anthropogenic forcings, the human changes, the deforestation, the pollution, the greenhouse gases, the irrigation, all of the things that we've done as a society. And then the blue is what happens when you put them all together. And if you look at each one of those lines, what you see is that all of the trends are related to our activities. Not the noise, but the trends. And the best match is, of course, if you use our the things that we've done and the things that nature has done on her own, and you put these things together, and we get a very good match to what's happened. From the top of the atmosphere to the bottom of the ocean, from the tropics to the poles. It's us. So why have things changed up until now? It's us. And the dominant thing in all of this is the increase in greenhouse gases, particularly carbon dioxide. So what's happening now? Mentioned the Antarctic a couple of times. Antarctica, is this blue line this year, has been incredibly low, outside of the bounds of anything that we've seen in the relatively short record that we have so far. We have good estimates of Antarctic sea ice from about 1979 onwards. We didn't really have great coverage before that. And for those of you who've been to Antarctica, you would understand why. It's not a very hospitable place, particularly in the winter. But the last few years have been exceptional. Very low levels of Antarctic sea ice. Temperatures have been literally off the charts. This is the surface air temperature, very similar to the first figure that I showed you, but this is daily data showing that, on average, the global temperatures have been warm, particularly since about May, June, July, record warm, October, record warm, November, likely to be record warm as well, right? Something's going on. The number of disasters and the costs of those disasters have been increasing, right? You can see that 2023, which isn't even finished yet, is already the biggest disaster cost that we've seen in this record. Now, there's a lot of things that are going on there, right? So we're building more things in more dangerous places. So costs are going up, even if the disaster, the physical climate changes were the same, but the physical climate changes are also changing. So flooding events are changing, fire events are changing, coastal flooding is changing. Heat waves are changing. And that's all starting to add up in terms of costs. And this is just in the US, let alone places that have more vulnerable or less resilient infrastructure. Most of those costs, most of those impacts are associated with what we call extreme events. So heat waves, extreme rainfall, flooding events. And where we have gone in to look at specifically those events, what we find is that all the places where we have a red dot, that's where we found a substantial and significant contribution from our activities, right? So the changes in climate that we have imposed upon the planet have made the chances of intense heat waves stronger, the chances of intense rainfall stronger, the chances of intense fires stronger. Not everywhere, not every event, but for an increasing number of events all around the world. So what does this mean for the future? Well, we can do some statistics here. This is the trend since the 1980s in the global mean temperature. The blue line there was what we predicted, what I predicted the temperatures would be based on what El Nino was doing at the beginning of this year. But in fact, El Nino has kind of shot up with a bang, and so now we're predicting that 2023 will be, without question, the warmest year on record. Right? It won't even be close. And because we're going into an El Nino, well, we're in an El Nino, and we're going into next year starting with an El Nino, that in fact is a great predictor of how much warmer 2024 is going to be. And so 2024 is going to be warmer than 2023. We're going to see a slightly different pattern of changes because of the El Nino becoming more established. But we can expect, you can expect, a lot of headlines from now, literally for the next, 13, 14, 18 months. You're going to hear this all the time. Record warming temperatures, record global warming, record impacts. But this is still within the bounds of the things that we expect, right? We do these simulations. There is noise in these simulations because of the chaos in the weather. There's an average that is the best guess of what's going to happen, but then every so often it's going to be much warmer than that. Every so often it's going to be a little colder than that. But right now, what's happening is still within the bounds of what we predicted. But there have been some special things that have happened this year, right? One of them that you might have read about was the Hunga Tonga eruption. So this is it was a subsea eruption near Tonga, and it was unlike any volcano that we've ever really examined, because instead of putting a lot of ash and sulfur dioxide into the atmosphere, it put a lot of water vapor in the atmosphere. And it put about 10% of the stratospheric water vapor just from one eruption. It increased it by about 10%, which is an enormous amount of water in a place that's very dry. I mean, it's like saying that it rained a lot in a desert, but obviously that's not a lot of water compared to the ocean, right? So the stratosphere is a very dry place. So increasing it by 10% is a big deal, but not an enormous amount of water in and of itself. But that's a greenhouse gas as well, right? So water vapor is a greenhouse gas. And so we've predicted that would have caused the climate to warm by about 0.05 of a degree Celsius. So that's not enough to explain how much warmer 2023 is compared to other years. People have also been thinking about how we've been cleaning the air. And we have been cleaning the air. We've been reducing the amount of pollution that we've been putting in the air because of things like the Clean Air Acts here in Europe, in Japan, even in China. China has been cleaning up its air at a prodigious rate. And then there's these new regulations that have been governing marine shipping. So ships used to use the dirtiest fuel that was available because it was cheap. And that was producing a lot of pollution that was causing cooling. And so as they've cleaned up their act since about 2020, then they've been reducing their pollution. And so in places where there are a lot of ships, the air has been getting a little bit cleaner, right? And people have been speculating that that might have caused a little bit of additional warming as well. But these are still small numbers compared to how exceptional 2023 has been. This is one of my favorite quotes. If we had observations of the future, we obviously would trust them more than models. But unfortunately, observations of the future are not available at this time. Right? We have to wait. And so when it comes to predictions, we really need models. We need credible models to do that. So what do those models show us? These are model simulations. This is from a model that I have worked with. The observations that I've shown you before are in the black. The model simulations for the historical period, that's in the purple there. And there's a spread, right? That spread is chaos, the weather, right? It's irreducible. We cannot predict the weather, more than a few days or perhaps weeks ahead of time. And so that spread is irreducible noise. But you can see that it follows what actually happened. And then what's going to happen? Well, we don't know what's going to happen, right? So climate scientists, we're not seers or fortune tellers. We can't tell you what the economy is going to do. We cannot tell you what technologies will be invented. We cannot tell you about geopolitical rivalries that might generate X, Y, or Z. But we can take storylines, scenarios that other people have developed and say, well, what are the consequences of those scenarios for the climate? And so we have 4 scenarios here, and they have technical names, but you can think of them as the one right at the top is the burn it all scenario. Literally, burn it all. Burn every kind of hydrocarbon you can find. All the coal, all the oil, the shale gas, the tar sands, all of it. Burn it all. And that's what might happen. And at the bottom there, you might say, well, maybe we shouldn't burn it all. Maybe we should stop burning it all. And so that one would be consistent with, say, net zero by about 2050, right? And so those are 2 quite different scenarios. And so that gives us a scope for what we are capable of doing, right? The burn it all scenario up at the top there, look at the numbers. 1, 2, 3, 4, 5 degrees Celsius. What's that in Fahrenheit? 9 degrees Fahrenheit. Okay, so burn it all, we could warm the climate as much as the Ice Age was cold in 100 years. Isn't that impressive? Yeah, yay humans. We are a geological force to be reckoned with. Yes, so this would be as warm in 100 years as the Ice Age was cold. That's a big deal. That would be a big deal. This is based on GCMs, but the storylines, the emission scenarios come from economists and integrated assessment models and those kinds of things. Oh yes, it doesn't stop in 2100, of course. Yes. No. There were theories along those lines back in the 1970s. There was this thought that if the oceans were warm, then there'd be more snow, and then that would trigger the ice. But nobody believes that anymore. So the timing doesn't work, and the process is that's not supported. But it was a thought back when we didn't really know very much. But then the stop burning it all, right? The 2 degrees scenario, right? You'll recognize that from what the Paris Accords wanted us to avoid. So if we get to net zero within a few decades, then we could stay below 2 degrees. We shall see, of course. So what's going to happen, though? We want to make our models better, right? So we're going to use the computing resources to do higher resolution runs, put in more detail, make it more complex, make it slower. We can combat that a little bit with machine learning. Machine learning is this wonderful tool that is not magic, though sometimes it seems like it. But in appropriate places, we can use it to better understand what's happening locally from what's happening globally. We can use it to make better physical parameterizations. We can use it to better tune the models, make them more realistic in the whole thing. And we can use them to do perhaps updates to those scenarios that I saw you on a much, much faster basis. So we have two things going on with increased computing, right? We're going to put in more stuff, but then we're going to find new shortcuts to make it faster. That's good. But we still need to do these massive ensembles. We need to be able to sample the weather states over and over and again, because if we want to get a good estimate of what's happening to the statistics of extremes, they're extremes because they're rare. And so you need to do a lot of computation in order to be able to sample those extremes. It's much harder than just doing the mean changes. We want to sample the uncertainty in the forcings. We still don't know what aerosols look like in a three-dimensional way around the planet. There'll be a new satellite that's launched in January called PACE that will be able to measure that for us for the first time. And so that might cause some reassessments of everything that's going on. And that's part of the more and better observational constraints, right? So we have been thinking very imaginatively in how we build these models. These models have lots of uncertainties going forward, but we can only bring them down, we can bring them in with better observations. And so as we go forward, we need to have not just better computers, not just better predictions, but we also need to have better constraints from the observations. So we need to have those things together, otherwise we don't really learn anything. So let's go back to those questions that I started with. Are things changing faster than we predicted? I don't think so, not yet. Ask me again in a year. But I think right now there's a combination of things that have kind of pushed things towards the edge, but I don't think it's predictive of that continuing without thing. I think within 1 or 2 years, we'll be back down along the line that we predicted. How are our predictions evolving? The basic predictions that we're making haven't changed since the 1970s. Increasing the amount of greenhouse gases in the atmosphere will warm the planet. It will increase heat waves. It will increase intense rainfall. It will increase rate of sea level. All of those things are just as true today as they were before. But we are being able to do better at making those big global changes applicable to what's happening here in New York, here in Chesapeake Bay, here in Antarctica, here in Europe. And we can localize these things in a much more useful way than we were able to before. So they're getting to be more detailed. They're getting to be more complex. And hopefully they're getting to be more useful. So what does that mean for where we go from here? That's the tricky part. People look to us as climate scientists as if we could tell them what's going to happen. We can't. We can tell you what the consequences of the things that we do, the choices that we make will be. And we're making, and we can answer those questions with increasing confidence. But we're in a very odd position as scientists. And there's this quote which I like to use that comes from Sherwood Rowland, who won the Nobel Prize for discovering the chemistry that led to ozone depletion. And he was quoted This is from the New Yorker. And this is after he won the Nobel Prize and had been very active to against ozone depleting substances, CFCs, you know, the aerosol cans and the like. And he said, what's the use of having developed a science well enough to make predictions if in the end, all we're willing to do is stand around and wait for them to come true? That's exactly where we are. We're supposed, as scientists, to take pride in the fact that we have observed the universe, we have encapsulated some key feature of the universe, used it to make predictions, and those predictions have come true. And we're supposed to feel great about that because it's a triumph of the intellect over nature. Except that when you're predicting things that you don't want to actually happen, you're conflicted. I don't want our predictions to be true. I don't want to be on TV every year saying, oh yeah, it was another record warm year. I don't want to be right about increases in extreme rainfall. I don't want to be right about the rate of sea level change. And yet, we are. And so we have this split, right? We're supposed to feel good because we're so clever, and then we feel shit because we're not clever enough to stop it. And so we don't just sit around. We talk to you. We talk to policymakers. We talk to school children. We talk to our families. We talk to people who aren't our families. We argue with idiots on Twitter. Why? I don't know. But that's where we are. Things are changing. We know why they're changing. We can foresee future changes. And we're right. And that sucks. So on that good note, I'd be happy to entertain any questions.